the adjacent graph, do the following. Part A is to identify a path of length 4. The key thing with this question is to respect the directed edges. I'm going to start at A, go to B, to C, back to A, and then to D. I've followed in the same direction as all of the edges. So for part A, I can say the path of length 4 is A, B, C, A, D. Part B says to identify a simple circuit of length 3. I'm going to start at A again, go to B, to C, and back to A. It has a length of 3, 1, 2, 3, and it starts and ends at the same vertex A. So a simple circuit of length 3 is ABCA. Remember, a simple circuit is a circuit that starts and ends at the same vertex and doesn't repeat any edges. Part C says, does path AED exist? And explain your answer. Let's look at it. It's asking us if we can go from A to E and E to D. When we look at the directed edges, we can see we had to go against one of the directions here when we went from A to E. So we can't go from A to E to D, even though they're stretched from E to D, even though that edge does allow us to do that. We would have been allowed to go from A to D, and we could get from D to E by following the parallel edge, because we're going with the arrow there. But that wasn't the question. The answer to C is no, because we're going against the directed edge. Question D. What is the length of path ABCADE? A to B, B to C, C to A to D, D to E. To calculate the length, we see we've got 1, 2, 3, 4, 5 edges. Not too surprising because there are 6 vertices identified in the path. Part 2 of that asks what is the length of path ADED? And in that case, we've got 1, 2, 3. Part E1 says what is the distance from A to C? Let's look at the paths that will get us there. To get from A to C, we can see that there are potentially a couple of paths, but of course we have to follow the directed edges. Go from A to B, and then B to C. In that case, we've got 2 edges involved, so the distance of D from A to C is 2. Next question, what is the distance from E to C? Let's see what paths will get us there. If we start by going from E to D, we quickly run into a dead end there, so that's not going to help us because we can't go from D to A. We're going against the directed edge. So I'm going to start by going from E to A. Again, I can't go back against the directed edge here, so I have to go up to B and then down to C. So that's one possible route, and that's a distance of 3. Let's see if there are some other possible routes. I could go from E, taking this route all the way over to B, and then I've only got 1 edge to get from B to C. In which case, that's a shorter distance. That only took 2 edges, so the distance is 2. The graph below is both weighted and directed. Determine the weight of path EDCAB. So we're starting at vertex E and we're going to vertex D. We've got to follow the directed edges. In this case, we can go E to D, D to C following the directed edge, C back to A, and A ending up at D again. The weight, remember, is the sum of all of the weights of each of the edges in that path. In this case, it's 2, 1, 4, and 6, which is 13. Now we're looking for the weight of the path BCAD. B to C, C to A back to D. Again, adding up all of the weights that were involved, we've got 3, 4, and 6, which again adds up to 13. One more path, EABC. E to A to B, B to C. Going in the direction of all the directed edges again, we've got 9 plus 8 plus 3, which is equal to 20. Part B says, identify all the simple paths going from vertex E to vertex B. Let's see what options we have. I'm going to go from E to A and A to B. If we add up the weights of that path, we see we've got an 8 and a 9, which makes 17. Try another path starting from E to A again. This time, however, I can't go down towards C directly because I'm going against the directed edge, but I can go down to D. So I'll go to D, then over to C, back up to A, and then A to B. In that case, I've got E, A, D, C, A, B. Now we add up all of those weights. We've got 9 plus 6 is 15, plus 1 is 16, plus 4 is 20, plus 8 is 28. What other paths have we got? Well, this time I'm going to start by going from E directly to D. I can't go up to A because I'm going against that directed edge. I can go to C, and back to A, and then to B again. And the weight of that is 2, plus 1 is 3, plus 4 is 7, plus 8 is 15. Part 2 of that question asks, of the paths you just identified, which has the smallest weight? It's not too hard to see that EDCAB with a weight of 15 is the smallest. Question 3. Based on the adjacent graph, determine the weight of path ABCF. We've got 1 plus 3 is 4, plus 6 is 10. We're asked for the weight of circuit CDEFC. 5 plus 7 is 12, plus 8 is 20, plus 6 is 26. The weight of a circuit of length 3 whose initial vertex is A. So we know we have to start at A, and we're going to do a circuit that has a length of 3. It doesn't give us many choices. In fact, there's only one choice. I guess it depends on which direction we go is the only choice we have. So in this case, we're going from A to B, which is 1 plus 4 plus 2, which is 7. Now we're asked to find all the simple circuits of length 4 whose initial vertex is C. So we're going to start at C and do circuits that have length of 4. We find C, D, E, F, C. It has a weight of 5 plus 7 is 12, plus 8 is 20, plus 6 is 26. We could go in the reverse direction, but of course the weight is going to be the same. But I can also go from C to F, F to A, to B, and back to C, which gives me a weight of 6 plus 2 is 8, plus 1 is 9, plus 3 is 12. And we're asked to find which one of the paths has the minimum weight, and it's not hard to see that CFABC, with a weight of 12, is the smaller of the two. Question 4. In the adjacent weighted graph, calculate, first of all, the weight of path ABCD. We've got 5 plus 3 is 8, plus 5 is 13. The weight of path BFCD, which is 4 plus 6 is 10, plus 5 is 15. Part C asks us, what's the distance from A to D? Remember, even though we've been talking about weighted graphs, the distance is the smallest number of edges it takes to get from one point to another, from one vertex to another. So we're looking for the shortest path, not the smallest weight. In this case, we can go from A to E and E to D. It'll give us a distance of 2. We can look at other options, and we can see we can also go from A to B and B to D, and it's also 2. We could also take paths through the center. They will have a longer length, so they're not considered the distance, because the distance is the path with the fewest number of edges. Similarly, the distance from B to D is going to be very simply 1. The first edge is from X to W with a weight of 5. The second edge is from W to Y with a weight of 6. The third edge is from Y to V with a weight of 8. The next edge is from V to X with a weight of 9. And finally, the last edge is from x to y, and it has a weight of 2. Question 6 says, in the weighted graph below, does the length of the path ABCD correspond to the weight of that same path? We're going from A to B, B to C, and C to D. We look at the weight, and it's 5 plus 9 plus 1, which is 15. But of course, the length of the path, there are only 1, 2, 3 edges. So the length is just 3. So clearly, the weight and the length are not the same. In question 7, we're asked to remove edges from this graph in order to obtain a tree in which the maximum distance from vertex F to each other vertex is 2. It'll take a little bit of experimentation to see what the graph would look like or which edges we can take out. We can see that if we go from F to E and E to A, we've covered those two vertices with a path distance of just 2. We can get to path D by going directly to it, and we can go to C, that's 2, and then we can also continue on to B. So with those edges that are highlighted in red, we're able to get to each vertex from F with a length of only 2. With that, it tells us we can get rid of this edge from A to B and this edge from E to D. For each of the graphs below, determine the number of edges that must be added to or removed from the graph in order to obtain a tree. Remember, the first requirement for a tree is that it be a connected graph. The second is that there are no circuits in the graph. Looking at graph A, we can see that we don't have a connected graph yet, so we're going to need to add in an edge to make it connected. We could connect either A to D or B to E, or we could make any connection we wanted, as long as we don't create a circuit. The same for graph B. As long as we connect everything and don't create a circuit, we have an acceptable solution. In graph C, the only vertex that's not connected right now is K. So we could connect K to J, or we could connect K to I. Either way, we're not creating a circuit, and there is no other circuit currently in the graph. In graph D, we have a circuit. We can go all the way around, so we need to take out any one of the edges, and it will make it a tree. In this case, it would take out edge from 5 to 4. In graph E, we actually have several circuits going on, so we're going to need to take out a few edges. First, we have a circuit that's running from E to A to D, and D to E. We're going to need to take out one of those edges, so it's no longer a circuit. Now we've also got a circuit here going from E to B to F to E. And similarly, there's also one from E to F to C to E. So we need to break up both of those circuits. The question is there any easy way to do that? And the answer, unfortunately, is no. Even if we take out the center edge, that still leaves a circuit going around the outside, going from E to B to F to C and back to E. So we could take out the center edge, but we would still need to take out one more edge. Again, there are multiple solutions that would get us there. We could simply have taken out those two edges, and we'd end up with a tree that way as well. Finally, in question F, we're in a similar scenario where we have two circuits going on, one here and one here. So we're going to need to take out some edges to break up both those circuits, and again, it's fairly arbitrary as to which ones you want to do. We could take out that one, and it would give us a tree. This graph illustrates the time in minutes that it takes to walk from one bus stop to another. Part A asks, how long does it take for someone to walk along the route ABCFD? We'll add up the weights. 5 plus 8 is 12, plus 10 is 22, plus 7 is 29. The next path is from A to E to F. In that case, we've got a 7 and a 5, which gives us a weight of 12. F, C, D, E has a weight of 10 plus 6 plus 13, which is 29. Each of those weights is designated in minutes. We can say that question A is 29 minutes, and question B is 12 minutes, and question C is 29 minutes. In question 10, we're looking at the roads that are connecting a series of lakes. They're trying to minimize their maintenance costs by reducing the number of roads that they have to keep running. Ultimately, what it really means is that we need to have a road that goes to each vertex, which in this case are the lakes. But we don't need any duplicate roads. Intuitively, if you think about it, it means you need at least one road that goes to every lake. And if we've got 1, 2, 3, 4, 5, 6, 7 lakes, that means we're going to have at least 6 roads. We shouldn't need to have more than that. Let's see how it works out. Since Lake F is the vertex with the most connections, I'm going to start with it and see if I can start eliminating roads that are connected to it. So I'm going to break this connection that goes down to Lake C, and of course I can still get to Lake C by going through Lake D or by going through Lake B, right? So wherever you're going, the point is there's still a road getting to Lake C, but we've still got 2 roads. We don't really need 2, so we could go ahead and get rid of that one as well. So that means we absolutely have to keep road D to C. I can take out this road connecting E to B, and I can take out the road connecting Lake A to B. That means that the road from B to G and from G to F also have to remain in place. Now I can see from that I've got 2 roads going out of Lake F. I've got one to Lake E and one to Lake D. So I don't need to keep both of those. I can get rid of one of them. It doesn't matter which one because we haven't been given any of the lengths of any of these roads. That means we need to keep road that goes from Lake F to D, and from D to E, and from E to A. If we do a quick count now, we've got 1, 2, 3, 4, 5, 6 roads servicing 7 lakes. To do that, we were able to eliminate 1, 2, 3, 4, 5 roads. The maximum number of roads that we can stop maintaining is 5. The following graph presents the length in kilometers of various routes that Louis could take as he trains for a marathon. He begins and ends each training session at his home. At the beginning of each training session, Louis runs less than 10 kilometers without taking the same road twice. Determine the route he can take and the distance traveled. We'll need to investigate some potential routes. Let's start at home. Go to A, that's 4, plus 3 is 7, plus 4 is 11. So we've already gone further than Louis wants to do in his short run. Let's try going from Louis' home to H, which is 1, to G, which makes it 3, and 2 home makes it 5. One possible solution is from home to H to G and back to home. And in that case, he traveled a distance of 5 kilometers. We can investigate whether there's another possible solution. We could go from Louis' home to H and then keep going out to E. So we're now at 1 plus 3 is 4, plus 5 is 9, but now we're still too far out, so that doesn't give us a solution. So it looks like the home to H to G and back to home is the only solution that'll keep us under 10 kilometers. Part B. What distance does Louis travel if he takes the following route? Home to G to F to E to H to B to A and back home. We add up the distances. 2 plus 8 is 10, plus 5 is 15, plus 3 is 18, plus 4 is 22, plus 3 is 25, plus 4 is 29. Identify 2 routes that would allow Louis to cover between 20 and 35 kilometers without taking the same road twice. Well, let's start going on one of those longer routes that we discovered at the start. There's 4, plus 3 is 7, plus 6 is 13, plus 9 is 22, plus 7 is 29, plus 1 makes 30. So one possible route is home to A, to B, to C, to D, to H, and back home. And it gave us a total distance of 30 kilometers. How about another route? Louis' home to H, there's 1, plus 4 is 5, plus 6 is 11, plus 9 is 20, plus 7 is 27, plus 2 is 29, plus another 2 is 31. Maybe there's one more. If we start at his home and go to G, that's 2, plus 8 is 10, plus 5 is 15, plus 3 is 18, plus 4 is 22, plus 3 is 25, plus 4 is 29. But Louis wanted a route that was between 30 and 35 kilometers, so this one doesn't work.